That's good.
Yeah.
Okay, so it's a pleasure to have Luis Fredes with us today, who will talk about almost upper directed Markov chains on trees.
Thank you very much. Thank you very much, Ines, for the presentation. We met in a summer school in Chile, so it was nice to meet you. And it's a pleasure to present these results that I did with Jean-François Marckert about almost upper-directed Markov chains on trees. So without further ado, I will go straight to the presentation. So to start, just to fix the setup of this talk, we will work with Markov chains. So there are transition matrices, which has matrices which has positive or zero entries, and such that each row sum up to 1. So you see here, this is just a representation. So from a certain state I, one could jump from I to I2, for example, or from I to I plus k with probability mi I plus k. And this is exactly what is represented in this probability. Okay. After that, I will use this just to fix the concepts, irreducibility, meaning that we have a path going from A to B in a certain number of steps with positive probabilities and vice versa. And for the whole talk, that I will assume irreducibility in my Markov chains. And I will talk about criteria to classify recurrence transients, positive recurrence, etc. So null recurrence too. So just to fix the ideas, recurrence is since I assume irreducibility, a Markov chain is said to be recurrent since one state implies that all states are recurrent. So it's the probability to starting from A, going back to A in finite time with probability 1. We say that the Markov chain is called recurrent, otherwise it is called transient. And this recurrence class, it can be subdivided into 2 categories, positive recurrence and null recurrence. Positive recurrence is that the expected time to go back is finite, and null recurrence is when it's infinite. And I will present some invariant measures. So just to fix the idea, an invariant measure is a measure that satisfies this equation here, which is called the balance equation. And we ask them to be positive in all the entries. Since we have irreducibility, we can assume this. So which kind of Markov chains I will talk about? These are this kind of Markov chains that we call almost upper or lower directed. So almost upper will be this kind of matrices U. Here I just put a graphic of the structure of a tree. So a tree is a graph which is connected and without cycles. And an almost upper directed Markov chain, if we start from the node, from the node U, we consider allowed the possible step to jump to the descendants, including U, and to the father. Okay, so here is a root, so we can talk about fathers and descendants. An almost lower directed will be if we can go to the children's of U and to the ascendants of U. And if you remark, this kind of Markov chains in the nearest neighbors random walks, so the ones that could go to the children or to the parent, these are included in both of these categories. So this is kind of more general. So we allow further jumps in the chains. Okay, so as it is, it's kind of artificial. So I will talk about the motivations that took us to this kind of chains. So these are the chains that are when we consider the tree to be n, okay, rooted at 0. So an almost over-directed Markov chain in this setting will be jumps which are allowed to go way further than I, for example, if we put the line the natural numbers, and we can go to the further when available. So if we are in the root, we don't allow this step because there's no further. And almost lower if we can go further to up to 0, and at most one jump to the right. And vertex processes are this kind of processes where you're allowed just to go back one step, further one step, and to stay in the same site with positive probabilities and all the other 0. So I don't know if you realize, but I use some symbols here, and these symbols look kind of artificial, and these are motivated by this kind of structures. So it's just to simplify the notation. So the transition matrix associated to this kind of chains has this kind of form. So the almost upper directed transition matrices are matrices without kind of almost upper triangular, the almost lower triangular, and the width of the processes are 3 diagonal matrices, transition matrices. So this is the motivation that took us to this step. So basically we did a first article where we studied with N, and after that we realized that it was even more general. So I say sorry because I use T here and I will use trees. This is the only time that I will use this T to denote a matrix. So just to finish the motivation, Karlin and McGregor in the 57 categorize this kind of chains in 2 aspects. First of all, they give an invariant measure. So they say that there is a unique invariant measure up to a constant factor, which is written as multiplication of quotients of these transitions. When we set P0 equals 1, this is just the constant factor that is hidden. And they say that if this measure is summable, so basically it could be renormalized to be a probability measure, it is positive recurrent. And recurrent if you have another criteria, and it's important to remark that this is not the same quotients that appears here, since here you have something started at j minus 1, and here something started at j. Here you have quotients started at j for both the numerator and the denominator. Okay, so what we did for n, just in order to motivate and in order to fix to show the notations of this. So we did a theorem that generalizes this result. So what we say is that in the case of n, if you take an almost upper triangular transition matrix, so this kind of Markov chains, there is a unique invariant measure, which can be when we fix P0 equals 1, you can write the invariant measure as a formula which depends on a determinant when you keep the lines and columns associated to the points from 0 to a minus 1, divided by the multiplication of the transitions going back to 0 from a. Okay, so it's j minus 1 up to 0. And in the case of n, this is the unique invariant measure of u up to constant factor. The chain is positive recurrent. It's still the same criteria that they have before. So if this measure could be renormalized into a probability distribution. So I won't write it because just stress the notation. And recurrent, if and only if we have these limits over quotients of determinants multiplied by one transition, okay? And we ask them to be equals to 1. Why do I motivate this result with this transparency? Is because we can recover from this result all the results from Karlin and McGregor, and these are not trivial results neither. So basically, to go from our results to their results, we have to use like combinatorial tools and some complex analysis in order to recover the results. But still, we can show that our results, when using U as a tridiagonal matrix, we can recover the results. So now what I will show you is what happens with trees. So, sorry, what happens with trees? I need to introduce them by explaining you how we construct an auxiliary kernel on this tree. So this is here I have the structure of a tree. This will be the ancestral line from you to the root. So this is what can be seen here. So what we do is for this auxiliary kernel. So for here I denoted by as a red arrow a possible jump for an upper directed kernel. And what we do is we construct an auxiliary kernel on this ancestral line, which does the following. Every transition that goes into one of the subtrees that has a first ancestor in this ancestral line equals to B will be redirected to it. So in order to compute the total mass, one realizes that this could be seen as like packing the weight or the transition probabilities that go to this red part will be all redirected to B. And this could be seen as the total mass in a difference of two subtrees. So I will denote TB, the subtree that it's the subtree hanging from B in this full tree. And this the total mass that we will redirect to B will be the total mass in B minus the total mass in this blue part. Okay? So just for formality, this could be defined in a proper way. So just to set some notation in the talk, the parent of U will be denoted as PU. The ancestral line from U to the root will be the set of this set of nodes. For a subset of nodes B, the total mass going to B will be denoted as UAB. The subtree hanging from A, it will be as I just said. And just let me leave this formality like this. It's just in order to show you that we can properly define these kind of things in a formal way. Okay? So the result in general trees states the following. So if you have an almost upper-directed Markov chain on a tree, the following measure that we call H invariant, and I will explain why we call it H invariant, where we fix the value at the root at equals to 1, and which is defined again as a determinant in the ancestral line up to the parent of U, divided by the transitions going back to the root, starting from U. This is one and not a unique invariant measure of U, even when you take it up to constant. The positive recurrent criteria is if we could renormalize it into a probability distribution. And the recurrent criteria is something that is similar of what we did in the case of N, but for every children of the roots, we ask kind of the same thing. Kind of the same thing is the same thing. Okay, sorry. And which is interesting from this result is that in the case of recurrence, you have that this should be the only invariant measure, just that not always renormizable, if we can say it. But this is the unique in the case, if one can prove that it's recurrent, this is the only one, okay? So what I propose is the following plan for the talk. I will give a half of the proof of this theorem. So I will present why this H invariant is an invariant measure for you. After that, I will present a method on how to compute the H invariant measure at a given point in kind of an economical way, if we could say like that, because it will only depend on the ancestral path values of this invariant measure. After that, I will explain why the H invariant can be seen as the invariant measure of a condition Markov chain. And I suppose the H invariant gives kind of a spoiler alert on the H transform of Markov chains. After that, we will discuss about the ends of a tree. So meaning that since in N you have just one invariant measure up to constant, and when you go to trees, you have that it is just one of them. Can it be seen as a discussion of the number of ends that tree has? And finally, some spectral properties of these Markov chains. So to start, a combinatorial warm-up. So to start, let me just say how we do in general to compute the number of spanning trees of a general graph. And this is given by the matrix tree theorem, which is due to Kirchhoff, which says that if you try to count the number of spanning trees of a given graph, you could compute them as a determinant of a given Laplacian matrix, where the Laplacian matrix is a diagonal matrix. This is this term, which says the degree of each vertex in the diagonal terms minus the adjacency matrix of the chain. And if you note, these Laplacian matrices, they sum up to 0 by row. So if you just take the determinant as it is, it will be 0. So basically the theorem says if you take the determinant of the Laplacian of this graph, but when you took out one line and column, and since we are counting just spanning trees, for this result, you can choose whatever line or column that you want, but the same associated to the same vertex, okay? So as an example, let me show you a graph. Here I explicit the Laplacian matrix of this graph. So basically, for example, from A to B, you have one edge. This will be minus the adjacency matrix. So this is the -1 that appears here. I followed the natural order for the lines and columns. So this is the connection between A and B. And for example, between B and C, you have two edges connecting them. So this is BC. And in the diagonal terms are positive, and it's equal to the sum of the rows in the adjacency matrix. So basically, this is a -3, and we put it with the opposite sign. So you see that every line sum up to 0, every row. And this matrix tree theorem, when we apply it to this Laplacian to this graph, I just picked the line associated to A to be suppressed with its column, and if you compute it, you could see that this has 98 spanning trees associated. So now I want to go to a generalization of this theorem, which is a weighted version of this thing. So to go to a weighted trees, I will consider rooted trees. So rooted trees have a canonical orientation, which is when you point all the edges towards the root. So basically, if you have a rooted tree, for example, I won't go to the example still. So if you have a rooted tree, you point all the edges going to the parent of each node when you identify the root. And as a consequence, these trees, this orientation will give that every vertex but the root will have exactly one outgoing edge from them. And now, how does a spanning tree of the allowed transitions look like? So here we have a background tree which gives the relation between nodes. So the allowed transitions are given by this structure. But what we want to count here is the weight of spanning trees in the allowed transitions. So just as an example for the setup of this talk, I just put here the structure of a tree. Here I put it in gray because I'm not using them in order to construct a tree, which is the graph that we are talking about here. The graph that we are talking about is the graph G, whose set of vertices are the same as the trees. That's why I I make the drawing like this, and whose set of edges are all the edges having positive transition probability with respect to you. So basically, a spanning tree of this kind of, in this graph, will be something that will have these subtrees, which are all pointing to this ancestral line in the original tree. And after that, I have to connect them in order to point towards R, okay? So basically, if you don't see it clearly from, from this slide, you just rearrange the parts of this tree, and you see that everything is pointing towards R, and that there is no cycle. Okay, so this is what we will do. We will count this kind of trees weighted, and which is the weight that we will consider for them will be the weight if you have a transition matrix M. This is a general theorem. This is for any weight that you could put, but for the setup of this talk, I will just consider M as a transition matrix. So the weights of a given tree when we use a transition matrix M will be the multiplication of the transition along the edges when you use the canonical orientation. So basically, in this example, this tree will have weight associated to the multiplication of, for example, M going from the root towards this vertex, and all the other arrows as we see here. So going back to the results, there is this generalized version of the matrix theorem, which says that the sum of the weight of spanning trees of this graph G rooted at R, this could be computed as the determinant of a Laplacian matrix. This is a Laplacian matrix, is still sum up to 0 by rows, where you put the identity, because if you use a transition matrix, the sum of the rows are equals to 1. You put the identity, you subtract your transition matrix, and after that, you have to erase a row and a column associated to the node R. So here, with difference to the kind of case of counting, here the root or the line that we suppress matters, and it matters how the row and line suppressed are the row and line associated to the root of the trees that we are counting in this formula. Okay? So this is the combinatorial matrix tree theorem, and there is a version for Markov chains, which is expressed in terms of the invariant measure, and it is called the Markov chain tree theorem, and which says that the invariant measure of a Markov chain could be expressed as the sum of the weights of spanning trees rooted at V. So if we want to know the invariant measure at a given point V, you can compute it as the sum over the spanning trees rooted at V according to the weight given by this the transition matrix, which has rho as invariant measure. And this should be renormalized in order to be an invariant measure. This result could be obtained in different ways. We explain it in one of the articles as, first of all, you can make a step with the Cramer rule, just in order to express it like this. And after that, you use the weighted matrix tree theorem, and you can obtain this result. Now, for the proof of why this H invariant measure, it's an invariant measure for our kernel or for a transition matrix U. What we did was to characterize the weighted rooted spanning trees on the graph of these Markov chains associated to U. Okay? So first of all, the previous result says that if you want to know the invariant measure of a given point, you need to explore which are the spanning trees rooted. If you want to know PU, you need to know you need to characterize what happens with the spanning trees rooted at U. And this is what we did. So a spanning tree seen from each vertex, it will be it will give the following decomposition. So if a vertex is, for example, inside one of these parts of the tree, so it's a descendant of the ancestral line in question, then imagine that you, for example, I will imagine that your node V, which is not in the ancestral line, so here is the ancestral line, imagine. Imagine that you don't connect it with the straight with its parent. So if it jumps to the descendants of him, then you know that the spanning trees that we are looking for, they have to be connected with the roots. They have a unique path connected to the root. So in order to go back to the root, they will be forced to go through B. So there will be lots of jumps inside of this part. But at some point, they will need to go back to this ancestral line in order to go to U. But if you do so, but basically you are closing a cycle, so it could not be part of a spanning tree. So basically, all the points that are not in the ancestral line, what you will have is that they are forced to take the arrows that connect them to their parents. Okay, this kind of arrows. So if a vertex does not belong to an ancestral line, it is forced to take this arrow, and this will generate as a forest with oriented edges. And this forest of oriented edges, now it just remain, in order to complete a spanning tree, it just remain to know what happens with the ancestral line. Okay? So now, in order to have something for the ancestral line, they could jump to the descendants, so they could make a jump like the red arrows. But every time that they are connected to one of these, the descendants, we can pack them in connected components of this forest, and we know that in this forest, there is a path going to the ancestral line, back to the ancestral line. So basically, if we contract these connected components of the forest, we could create a jump to this connected component, and we know that there will be a path that could make like the combinatorics in order to construct to complete this random forest into a spanning tree. So basically, there is a factor that will be added due to the forest, and the other factor will be the ways to connect the ancestral line to this random forest. But when we contract them, basically we are just constructing a tree in the ancestral line where we translated the transition probabilities to go to these components of the forest as the matrix UU, the auxiliary matrix that we did before, because we are reducing our problem into something just for the ancestral line. So basically, this is what we did. This decomposition led us now count the weight of the spanning trees rooted at a given node of the tree. So the sum of the weight of the spanning trees in this graph with transitions, they will have two factors, one coming from the forest. These are the blue edges that I drew before. And for the other part, for the red edges, what we will have is something that is counting the spanning trees on this ancestral line when we modified our kernel and we put our auxiliary kernel. Up to this point, we have an expression, but now we want to get rid of this part. And why is that? This is just because we could renormalize by the weight of all the transitions going to the parents in the tree. And this will just have the difference that we will have the transition on the ancestral line going to the parent. And this is exactly what we did here. So C is the full multiplication of this descending step going back to the root, and we just keep the transitions in the ancestral line. Which is important of this renormalization is the fact that this quantity does not depend on the transitions that are outside this ancestral line. We just care about the transitions in the ancestral line, and the transitions which are going to the outside of the ancestral line, they are just kind of gathered in this UU. Okay, so these computations are kind of nice to work with, and I will show you why. So the Markov chain tree theorem says that there is a renormalization constant in order to make this the invariant measure of one of the invariant measures of the chain. Here we are working up to this point. Everything is valid if we work in finite trees. So this is why I just isolated for finite trees up to this part. Since spanning trees, since the tree is finite and we assume irreducibility, this is the only invariant measure that it could be that the chain has. And to go to infinite trees, what we will do is the following. So if you write the balance equations at a given vertex in an infinite tree, you will notice that for a given point u, it will just depend on the ancestral path and in the children's that it has. And this is from the nature of almost over triangular, almost over directed random transition matrices. So now what we will do is to show that PU, the H invariant measure that I defined in the theorem, satisfies this system by using an auxiliary irreducible Markov chain on a finite tree. And this finite tree, what will be is, I will show you, I will present it with the picture here. So basically, we will truncate our matrix up to 2 generations further than the node U. And what we will do is just to transform it. If we go further than 2 generations after U, what we will do is we will redirect those transitions to the first ancestor going to the root. Okay? This restricted transition matrix coincides with U up to generation U plus 1. So all the transitions here, acting here, they are the same for U when we truncated it than with the chain in the infinite tree. And this gives, since we already solved the problem for finite trees, and we know that P for the truncated matrix is an invariant measure, we obtain that the system in 1, the equation in 1 is satisfied when we truncated our matrix. And this is the same equation satisfied by the infinite tree when the transition kernel is not truncated. Okay? So with this auxiliary tree and Markov chain, we could show that the system is satisfied for every U in the infinite tree. So this is an invariant measure of the infinite tree. Now I would like to go, this is the end of the proof, and now I would like to go to different discussions about this invariant measure, Markov chain, etc. So the leaf addition strategy. This is what I said before, that it's a strategy in order to compute the invariant measure of a given vertex without having to compute the full invariant measure. So assume that you have two trees, infinite or finite trees, and that one could be obtained from the other. So tau prime can be obtained from tau by the suppression of a leaf. Okay, so they just disagree in one leaf. And assume that there are two transition matrices, one associated to each tree, such that they coincide when they start at T prime and when they go up to the points that they have in common, and when the transition matrix goes to L, to the leaf that is not present in tau prime, the transition matrix in tau prime, what it does is that it will redirect it to the parent. Okay? So this is kind of a reduced transition matrix. And a proposition that we prove is that basically, and one left eigenvector of this transition matrix U prime can be extended with this formula. So to obtain a one left eigenvector of the biggest transition matrix, what you do is that you compute along the ancestral line, you take the values of the invariant measure that you already computed for U prime, and you take this quotient, you compute this, and this will give you the invariant measure associated to the leaf that was not present in the tree, which the smallest tree. So how do we use it? Because as this, it could seem a little bit constrained. So what do we do? It's morally, from our proof, from the proof that I just presented, we see that UU, this auxiliary kernel, has the same invariant information as U on the ancestral line. So we will take advantage of it. How? Imagine that we use T prime, so as a smaller tree, which will be just the ancestral line of up to the parent of U, with a transition matrix U prime, which it's the auxiliary matrix in this part of the ancestral line. So basically, is the Markov chain on the auxiliary with the transition kernel, which is the auxiliary kernel here, and we will extend it up to a leaf, to a new tree. So we will extend it one step further, and we will take a tree which is one node bigger, which will be a leaf, which is U, with a transition kernel UU. So this is the auxiliary transition kernel for this matrix. And if you remember, the mass associated to jump to PU for the smallest tree, it will be the full mass of this part. And for the extended one, the biggest tree, it will be just the mass going to this part minus the mass going to this part. So basically, this translation says that our transition matrices, they satisfy this condition. Applying this proposition to this example, give that we can compute the invariant measure at a given point from the ancestral line when taking the transition probability to go to the leaf, and in this case, the leaf is concentrated the mass of the subtree which is hanging from U, and with the step going back, as in here. Okay. So now, just in order to show you that it's in the practice is kind of helping us. I will just present an example. So consider a finite tree T and a Markov chain such that starting from a given point, we could jump to the parent when available, or a descendant uniformly at random. And here we are using a finite tree because in order to have a finite number of descendants, we will set the invariant measure at equals to 1 at the root. And if we apply our formula for the leaf addition, we see that this transition matrix from this description, it takes this value, which is going from B, which is one node in the ancestral line, to the tree hanging from U. It will have mass, the number of nodes in U, divided by the mass of the tree hanging from B. So here we are computing. Imagine that you have a V here, and we want to know which is the total probability to go to this part. So this is the numerator, this is this transition probabilities, and this is the probability to go back to the parent. And now, if you reinject this formula for row V, you can make the exercise, and this led us to compute the full invariant measure. So the invariant measure for this kind of transition of Markov chains is given by this form, this closed form. So we have access right now, and we give like at least 5 examples of Markov chains, even with infinite trees, where we can compute a closed formula for these invariant measures, since the determinants are not quite nice to work with. But this leaf addition strategy gives us a tool in order to compute this kind of invariant measures. Now I would love to talk about some other properties of this Markov chains. So why did we call this invariant measure the H invariant? So this is because it could be seen as the invariant measure of a condition Markov chain. So suppose that you have a finite subtree of the full tree, and we define ht of u, which will be the probability starting from u to go back in finite time to t. Okay? From this description, we could define a Dup's H transform of this matrix, and this gives us a matrix u tilde of t, which acts in the full tree, but which gives the following transitions. So u tilde coincides with u if you start at I in t, and if you start from another point, what you will do is to take this quotients of H, so these probabilities that I just defined, and you take the transition as in the original matrix. So this form is the important part. And the Duph transform, what it does is it forces the matrix to go back to T, in this case, to small t. So basically, what we obtain from it is that this is the invariant measure of this small t of u tilde must coincide with p on the interior of t. This is why. This is because the balance equations associated to this kind of matrices just depend up to the children's. And the second is that the invariant measure is unique since this chain is forced to be recurrent in some sense. And the conclusion of this is that if you take a sequence of finite trees growing to the full tree, you have that this, for every u, you will cover it at some point. So basically, this gives you the interpretation that this is the invariant measure, this limiting measure is the invariant measure of a Markov chain conditioned to come back to any finite tree. Okay? So the take-home message is that the H measure is just the invariant measure of u when forced to be recurrent in some sense. Okay? So now, how much time do I have left? think that is 5 minutes or so.
Yeah, I would say 5 minutes.
Okay, so let me just go to some other discussions about these Markov chains. First of all, why when we take the tree equals to the natural numbers, the invariant measures is unique. And this comes from this expression. So if you write the balance equations for this Markov chains, when you take the tree to be n, you will have something like this. And so they depend up to b plus 1, which is the unique children that it has in n. And this gives you the following expression that led you to compute the invariant measure at a given point by the previous values. And this is a unique way in some sense to do this. So this gives you the uniqueness of the invariant measure. And this is why we can discuss about ends of a tree in order to generalize this result. Why, when you take general trees, this is not the unique invariant measure. So what we did is that we consider a restricted chain. So if you take an infinite path, so this is an end in a tree, it's just an infinite path. We could define a transition matrix UP. So when you take this infinite path, you define a transition matrix acting on a tree TP. The tree TP will be the infinite path together with the finite trees hanging from it that does not belong to another infinite path, okay? So this is a proper way to define it. And basically what you do is to redirect all the transitions that go outside this tree TP. You redirected them to the first ancestor which lives in TP. So once you do that, we obtain the following theorem, which says that an irreducible transition matrix, upper directed transition matrix on an infinite tree with a finite number of ends, it will be recurrent if and only if for every n, the matrix UP is recurrent, and positive recurrent with the same mechanism. So for every n, UP is positive recurrent. And this just works when there is a finite number of ends. So I will discuss what happened with an infinite number of ends. To start, some remarks. The positive recurrence cares about finite trees, meaning that one could create examples of infinite trees where you have finite trees hanging from these infinite paths, and you can put every time like bigger and bigger trees hanging. So basically the expected time taking to return, it will forcibly depend on these finite trees. So one cannot neglect them in the positive recurrence case, but in the recurrent case, we can't forget about these finite trees. We just redirect arrows since we know that we will come back from finite trees. So we can study just the trees for the recurrence. We can just study trees which consist on infinite paths, okay? So this is our first remark. And what we obtain is in the infinite number of n setup is that if you have an end, so an infinite path and this restricted transition matrix in this induced by this n, if you have one that is transient, the matrix will be transient. We try to prove the reciprocal, but this is not true. So basically in the paper, we present an example in the complete infinite binary tree, where you have that all these restricted transition matrices are positive recurrent, but the original chain is transient. So basically it killed all the hope that we have to try to characterize something about it. And the last part of the discussion that I wanted to have with you is that is the number of invariant measures related in some sense with the number of ends having a transient UP? So what we could answer of this is that we can't give a criteria depending on the transience or not of UP. But what we could say is that the one left eigenspace, so here is when you take measures with signs into account, the one left eigenspace has a dimension that is related to the number of bifurcations of the tree, which is just induced by the number of ends. So you reduce your trees just with the infinite path that you have, and you count the number of bifurcations that it has. So the dimension of the one left eigenspace could be characterized as a function of this number of bifurcations. And obviously this bounds the number of extremal invariant measures, but it is difficult to discriminate which ones are the good ones, because we have to restrict with the ones that just have positive, non-negative values. And the last result related to this is that, can we say something about other eigenvalues? And what we prove is that, yes, we can say something, but there is a special behavior for leaves. So if you have an upper-directed irreducible transition matrix on a tree, which has no leaves, so imagine that it's just composed of infinite paths. Then we have that all complex value is in the spectrum of these transition matrices, and there is one eigenvector that we could explicit. So this is equals to, we fix it equals to 1, but it's basically the same that we computed before. It's just that we add a lambda here right next to the identity. Okay? And what we obtain is that when you add leaves, you had kind of an abstraction in order to test if a value is an eigenvalue. So I won't go further. I think I don't have any time left, so I will end my talk here. Thank you very much for your attention.
Thank you for that. Thank you very much.
Sorry.
Questions?
So for this type of change, if in the case of which you don't have a uniqueness of invariant measures,
Yeah.
do you have something like a selection principle? I mean that if you look this chain at a long time, you select one of these invariant measures, and this is what describes the behavior of the chain, or something similar?
No, in fact, the behavior of the set of invariant measures, it's really super weird. We give a lot of examples in order to try to find which was the limitation that they give us with the number of invariant measures, but there is no a clear principle of which one is dominating the behavior of the system at a given point, nor which are the chains that possess more than one even. Imagine that you have a chain that is transient, the reduction to all the ends is positive recurrent. We couldn't even answer the question of which kind, because this restriction to ends is at some point, if the chain goes inside these branches, they should be dominated by the behavior of an invariant measure that it's kind of dominating this zone. in some sense. But we can't really characterize it. It's really an intricate behavior for this kind of chains. We try to tackle the problem for the point of view of the extremal invariant measures that we could look for or try to characterize, but it's really complicated. And at some point we try to tackle it with the reverse Markov chain that it could induce. So we try to study what happens with almost lower directed Markov chains, and they have a similar behavior. They could have lots of invariant measures. They behave. There are something to study there that we couldn't understand for the moment, but we are trying to tackle that kind of questions.
You.
Hello, Pablo, how are you? If you have the infinite or maybe all infinite ends to your space, then you would have a Markov chain that will stay in the space, and you could look at the quasi-stationary distribution.
Of course.
That the distributions conditioned not to go to those points.
Okay.
Maybe you could look from this point of view. It's not exactly the same because you need infinite time to arrive to those points, but it looks similar problem.
At some point we try to study what happens with quasi-stationary distributions, and basically this is where we get to this H transform interpretation. I know that they are not linked directly, but we try to study what happens when you force it to stay in a region, and basically that's where we find that. But for the quasi-stationary, we didn't. I think that we tried to tackle the problem and we didn't get where to tackle the specificity of the problem with the quasi-stationary. It's true. You can tackle the problem with that, but we didn't go further in that direction. Maybe it's a good clue to try to continue with this, with the perspective of this work. But I don't have any direct answer to that question for the moment.
Thank you. Something that you can do if you want to simulate these things is just to you let the system go. At some point you say, well, we have arrived at infinity with some condition. And then you come back with the empirical distribution up to this time. That like paper by Anderson.
Okay, that reference interests me. So thank you very much. We can exchange afterwards in order to have it. Thank you.
Any other questions? Luis, I have a question of my own. Can you say something about what happens if you take a Galton-Watson supercritical conditioned on non-extinction? Do you know what happens there?
We did one example of that kind in the paper. The expressions are kind of twisted. We give a criteria in order to be recurrent, things like that. Exploiting all these techniques that I just presented. But there is not something close. We took a lot of directions to study this kind of chains. This is just one of the applications that we put. And yeah, there is a random environment together with the chain, but we could characterize something there if you are interested. But the expressions are not that nice to present in this talk, but Yeah, we have some criteria there.
Okay, maybe I can ask you later.
Yeah.
So if there are no further questions, let's thank Luis again.
Thank you very much.
All right, and we meet next week.
Thank you. Bye, everyone.
Thank you. Okay.